Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we'll give a little bit of an idea behind chapter 14, which gives a complex analysis contour integral extension of Pick's theorem. I will assume some basic complex analysis. In particular, I will assume that you know how to do contour integration via residues and the residue theorem. The main idea of this chapter is to design a complex function which has a pole at each integer point if you want in a complex plane. So each point for which both the real and the imaginary part are integers with residue 1 such that this function is doubly periodic. We'll say in a moment what that means. The Weierstrass zeta function that you see here almost does the trick. So you can see the definition here. Basically what you have is you're producing a pole at 0 and then at each Gaussian integer, so each complex number with real and imaginary part integers. And the additional terms here are designed in such a way that the infinite sum converges nicely. You can realize again, so that this function is analytic everywhere except poles at every Gaussian integer with residue 1. We'll need another property, and the Weierstrass zeta function does not have the property just yet. Namely, we need the definition of a doubly periodic function. This is a complex function and doubly periodic means it's invariant under translation of the variable by 1 and by I. Well, I should really say this defines a doubly periodic function with periods 1 and I. You can imagine that there's a more general definition here with two somewhat arbitrary complex periods. I said earlier that zeta almost does the trick. This lemma that you see here, lemma 14.4, tells you that we're off just by a term, some constant alpha times the conjugate of z. We are producing a slightly new function here, which is not quite analytic because adding this z conjugate has a little bit of an issue, but this will actually be helpful in the main theorem of chapter 14, as we'll see in a moment. But for now, it's also helpful in the sense that this new function now, you can prove, is doubly periodic. One can prove, and all of these details are in chapter 14, that this alpha here is the number pi. The main ingredient for this lemma is what's called the Weierstrass p function. So this is the derivative of the Weierstrass zeta function up to a sign. And again, this will be a function that's analytic everywhere except for poles at Gaussian integers. Now these are double poles, but one advantage of the p function is that it is doubly periodic from the start. At any rate, so to prove lemma 14.4, you can imagine that we will write the zeta function as some sort of integral version of the p function. And then to make everything work out correctly, we have to add this term pi times z conjugate. These are all the ingredients we need for theorem 14.5, which we think of sort of a complex counter-integration version of Pick's theorem. We have a curve that avoids the Gaussian integers. And now integrating this function that we constructed on the previous page over this curve gives you up to the usual complex analysis factor of 1 over 2 pi I, the number of interior integer points minus the area of the region enclosed by the curve. So we think of this as an analytic version of Pick's theorem because we're picking up precisely the lattice point count and the area of the curve. But in some sense, this is much more general because we're not making strong assumptions about the curve C. In particular, it doesn't have to be a polygon. I should also remark that one can sort of get around this condition if we're careful. And in fact, Pick's theorem, which we discussed in chapter 2, does follow from this theorem, but one has to be a little bit careful and study contributions of integer points on the curve when we relax this condition. At any rate, let me give you just a very brief idea of how this theorem follows. It's actually not a long proof. What you do here is you split this integral up into, well, we have 1 over 2 pi I times the integral of the zeta function. And because the zeta function has residue 1 at each integer point, this will be by the residue the number of integer points inside the curve. And then the other contribution, if we take out this minus pi, we have an integral of 1 over 2i with a minus sign. And now we're integrating the almost analytic function z bar. And we're claiming this is negative a, so you're picking up exactly the area over here. And this follows from Green's theorem. This is maybe something you've seen actually in a complex analysis class, because z bar is one of those functions that I can integrate even without the residue theorem, sort of from first principles, and Green's theorem helps.